Okay, so we should be live. Check, see who we've got. I've got, okay, just Andrew, looks like. But others should be able to join as we go. Throw you over to the other window so I can see if anybody else joins. Alright. Oop. Broadcasting to the window you can't see. Just change that really quick. Primary monitor. And go. Alright. So I'm going to quickly review some curve sketching stuff. So for this first one, I've got this function that is differentiable on the interval from -4 to 7. The graph of the derivative has 3 semicircles and 3 line segments shown below. The first thing I want you to do is find the x-coordinate of every critical point of the original function, which is not what's graphed. What do we need to do?
I should find the point where f prime x is 0.
Okay, so for this graph, what are the 2 points where f prime x is 0?
-2 and 6. Yeah, 6.
Okay, -2 and +6, because this graph is already f prime x. Looks good. So it says justify your answer. We could just say because the f prime x is equal to 0. For the x-coordinate of every relative extrema, label each as a minimum or maximum, and then justify your response.
So when x is less than -2, the f prime x is negative, and when x is greater than -2 but less than +6, f prime x is positive. So -2 is a minimum.
Okay, -2 is a relative minimum. Looks good.
And if x is greater than +6, f prime x is negative. So x equals +6 is relative maximum.
Perfect. And then f prime x equals 0 when x equals -2 or 6. Alright, find the open intervals where the function is increasing or decreasing and justify your answer. I believe you kind of already told me, but if you could just tell me which ones are increasing, which ones are decreasing then?
From x from x greater than -4 and but less than -2 is decreasing because f prime x is negative. And from x equals -2 to x equals +6 is increasing because f prime x is positive, and x less than 8 but greater than +6 is decreasing because f prime x is negative.
Awesome. Decreasing as f prime of x is positive. Okay. Then find the x-coordinate of every point of inflection and justify your answer.
Point of inflection. Point of inflection means f prime x is now 0 and the sign changes.
Yes.
So when x equals 0, slope of f prime x is 0, indicating f prime x is 0.
Okay.
And also same for +3.
Cool.
Does positive 5 counts as well, or is it just...
Our sign does change at positive 5.
Oh,
So I believe positive
but
5 would count as well.
oh, okay. They're also positive 5.
Okay, so f prime prime changes sign at x equals 0, 3, and 5. Okay. Find intervals of your concavity, so concave up and concave down, and justify your answer. If you're talking, I think you're still muted.
Okay, sorry.
That's okay.
In order to know concavity, we have to know whether f prime prime and x is positive or negative.
All right.
So from x equals -4 to 0, the f prime prime x is positive, so it's concave up.
Okay. Are there any
And
other intervals where we are concave up?
from x equals 3 to x equals 5.
Okay, so that's -4 to 0 and 3 to 5.
Yes.
Okay.
And from 0 to 3 and 5 to 7, it's concave down because m prime prime x is 0. I mean less than 0.
Okay. And then from 7 to 8, we are neither, since we have concavity of 0.
Okay.
If f of 6 is 5, what would our equation of a line tangent to f of x be at x equals 6? What's our equation of a tangent line first?
Y minus, when we have to find tangent line for a comma minus b equals f prime of a times x minus a.
Okay, so y minus b, you said, is equal to f prime a x minus a. What is b, what is a, what is f prime a?
Our b is 3 and our a is 6, and f prime a is 6, 0.
Okay. So if we simplify, what's the equation of the tangent line?
Y equals 3.
Y equals 3, perfect. Don't know if I can write that low. Y equals 3. All right, awesome. What about f prime lets you know if the graph is increasing?
F prime is positive.
Okay, if f prime is positive. So if we're decreasing, f prime should be...
Negative.
If I'm concave up, what happens to f prime prime?
Negative. Positive.
Positive, and concave down.
Negative.
What happens to f prime if we're concave up?
F prime concave up. Doesn't matter.
It does matter, but the answer is not just going to be positive or negative.
does when it's increasing.
Increasing, perfect. And when we're concave down then, should be
Decreasing.
decreasing. Awesome. Okay, I don't know if this is new. I think I've done this with one class and not the other, so I can't remember which one's which, so this might be new stuff, I'm not sure. But I want to talk about separable differential equations, which are a new type of equation that we use when we're talking about real-world population growth. In middle school, you may have talked a little bit about exponential growth when you were talking about things like bacteria in a petri dish. And your equation looked something like this, right? Where the amount of bacteria kept splitting again and again and again over time. And the problem with that model is if that was actually true, then bacteria that split really fast, like E. coli, would very quickly fill up all the space on Earth. And thankfully that's not the case. In the real world, environments usually have constraints. So even for things that start growing exponentially, there will be some sort of limit based on the food or water or space or other constraints that your environment can support that will eventually stop your population from growing exponentially and start causing it to grow logarithmically up to some form of upper limit, which I'm going to call L. So in our petri dish example, I would start with maybe one bacterial cell in a petri dish that can divide and split in order to fill up that amount of space that we have in the dish. And it keeps dividing and splitting until eventually we fill up half of what the petri dish can support. And now we can't keep splitting exponentially anymore. So the bacteria that are touching each other stop splitting. We have less and less and less bacteria that are splitting until we eventually fill up the entire petri dish with bacteria. Any questions on the concept?
No.
Okay. It is much easier to define these separable differential equations in terms of their derivative rather than in terms of their population. If we take a look at our graph right now, our slope is approaching 0 when our population is 0, and our slope is approaching an upper limit when our population is the upper limit, right? So if we take a look at this first equation, this is the change in population over time, is some sort of constant k times our population. So when p is 0, this part is 0, and the whole slope is 0, times 1 minus our population divided by the limit, when our population is equal to the limit, so when p equals L. Then this will be L over L, and 1 minus 1 is 0, which will give us a slope of 0 as our population approaches the upper limit. The same thing happens here as well for this version. Kp times L minus p. If our population approaches L, then L will be p minus p will be 0, and the derivative will be 0, so the slope is 0 as we approach the limit. If p itself is 0, then the slope is 0 as well. Okay, so we call this upper limit the carrying capacity. Carrying capacity is the maximum limit that an environment can support. So if you see it on any of your FRQs, that's really what they're referring to. We have a couple students that want to go into environmental science later on. And this is a type of equation you'll see a lot in environmental science when you're talking about how much your population of a particular species could be supported in an environment. Okay, so here's one more time graphically. We're changing from a slope of 0 when our population is 0 to a slope of 0 when our population is at an upper limit. This also means that halfway between 0 and our upper limit, we'll reach our fastest growth rate. So that's when the slope is as large as possible. We'll always be at L over 2. Any questions so far?
Nope.
Okay. If I derive this again, then we can take a look at our second limit in order to figure out, just to prove that that L over 2 is our fastest growth rate. So if I derive this equation that I have right here, P is really my only variable, so if I derive P in terms of T, I'll end up with K, my constant, when I derive Kp, times L minus P, and then with product rule, plus Kp times -1. And when we simplify, that gives us KL minus Kp minus Kp, or K times L minus 2P. So if we set the second derivative equal to 0 to figure out when the fastest growth rate is going to be, then this will equal 0 if I divide by K whenever L is equal to 2P. And if I divide by 2 on both sides, then my P would be equal to L over 2 at the point where our second derivative is 0. So if my concavity is 0 and our slope is positive, then we would have maximized our slope. When we maximize anything, we derive it set it equal to 0, solve for our variable. I would have maximized my slope at that point. Any questions on our proof?
No.
All right. So here's a sample question of what something related to logistic equations could look like. I've got a population of rabbits in Australia growing according to this differential equation below. So I've got a differential equation here. And I've also told that a population of rabbits and billions of rabbits at any time in years after their introduction is, we have 500 million rabbits 10 years after the rabbits were introduced. Okay, so the first one, I want to know how large will the population of rabbits be when the growth rate is the fastest? Okay, so to answer that, we need to figure out what the maximum population would be. Taking a look at our first derivative here, when our slope is 0, I will either be at the lowest or the maximized population. So what two p-values give me a slope of 0 right now?
When P equals 0 and P equals 10.
Okay, so the maximum that our population could be is 10 right now, which means we could approach 10 billion rabbits total in Australia. But after that, maybe there's not enough food in all of Australia to support more population growth. Okay, we proved in the last slide that our second derivative is 0 when our population is our upper limit divided by 2. So if our upper limit is 10, then our fastest growth rate will happen when our population of rabbits is how much?
Okay, what was the question? When P equals 5?
P equals 5. Or 5 billion rabbits. Okay. For the next one, number 2, we want to create an equation modeling the number of rabbits at any time in years after the rabbits are introduced. So for this one, we would need to solve the separable differential equation in order to create a new equation for P in terms of T. I'm going to walk through this first one really quickly. So the first step that we need to do when we're solving a separable differential equation problem is to separate our variables. So I'm going to move all of my P's to one side and all of my T's to the other. So if I move all of my p's to the left right now, I can divide by p on both sides and divide by 10 minus p on both sides. So it'll give me dp over p times 10 minus p times dt on this side. I can also multiply by dt on both sides in order to get all of my t's on the right side. So now I've got dp and dt on the top of their fractions, respectively, which is going to allow us to integrate. Now, unfortunately, 10p minus p squared isn't something that we can just use a u substitution for, because we won't get the right powers of p for the numerator that we need in order to integrate directly for our u prime. So what we need to do is partial fraction decomposition. So for partial fraction decomp, as a quick refresher, right now I've got 1 over p times 10 minus p on the left side. If I wanted to break this apart into two separate fractions where I had some constant over p plus some constant over 10 minus p, then I could add those two parts of the fractions together in order to get my total 1 over p times 10 minus p. So that means there is some constant a and some constant b that we could solve for. In order to set up an equation that we could use to solve for those two constants, we could cross multiply to give us a common denominator, and that should give us the same numerator when we add our two cross multiples together. So that gives us an equation 1 is equal to a times 10 minus p plus b times p. And we can use that to solve for a and b. Since a and b are constants, we can plug in any p that you want. And this equation should still be true. So right now, if I want to solve for a, I can plug in p equals 0, and that will cancel out my b term. If p is 0, I'll get 10a equals 1, so therefore a is 1/10. If I want to solve for b, I could plug in 10 for p. 10 minus 10 is 0, 0 times a is 0, so I'm left with b times 10 equals 1, where b is also 1/10. Okay, so now I can replace this whole side of the fraction with this, where a and b are 1/10. So that gives us this new equation on the left side. Are you okay with our partial fraction decomposition and separable differential equation so far?
Yes.
Yes, okay. So from here we can integrate normally. 1 over a variable when we integrate is the natural log of our variable. I can do a u substitution here, so 1 over 10 minus p. When I integrate, should give me the natural log of 10 minus p times negative 1. We also had our constants, 1 over 10 from both a and b on the outsides. When I'm combining two logarithms of the same base, in this case a natural log, if I'm subtracting two logarithms of the same base, then we can divide. I've also multiplied everything by 10 in order to get rid of this 1/10. So if I multiply through by 10, the 1/10 goes away, the 1/10 goes away, the t over 500 becomes t over 50, and c times 10 is still a constant we haven't solved for, so I can leave that as c for now. Then I can raise both sides to a base of e after combining my logarithms with my quotient property of logarithms. I can multiply by 10 minus p, distribute our constant e to the t over 50 into both terms, add my p term back, factor out my p, and divide by what's left, and we get a new equation for the population at any time. Okay, so as you can see, this population equation is a little bit crazy. From this point, I would need to plug in the point that we were given. When t is 10, our total population should be 1/2. In order to solve for c, and then after solving for c, I would get a general form for the population at any time that we could use to plug in any t we want and get our population. But these logistics equations are much easier to define in terms of their slope than they are in terms of their population. Solve this last one. Determine how many years after the rabbits are introduced it would take the population to reach the fastest growth rate. So we said our population will reach the fastest growth rate when p is 5. So what we need to do is we need to plug in our point, get our form for this equation. Once we have a general equation, p at any time t, I'll plug in p equals 5 and we'll solve for t. So right now, I'm going to plug in this equation. This value into this equation. So P is 1/2. Equals 10 over 1 over c e to the t, which is 10. So this is 10 over 50, or 1/5, plus 1. And now we can solve for c. I think I'm just going to multiply both sides by the whole bottom part. I'll also multiply by 2 on this side. So this is 20 is equal to 1 over c e to the 1/5 plus 1. I can subtract 1 from both sides, so I've got 19 is equal to 1 over c e to the 1/5. Multiply by c e to the 1/5 on both sides. Now I've got 19c e to the 1/5 is equal to 1. And then divide by everything that's not c. Okay, and now that I've got my c term, I can plug that in to get a general form for our population. So therefore, our population is equal to 10 divided by 19 e to the 1/5 over e to the t over 50 plus 1. Okay, and then from this point, we can set p equal to 5 and solve for t in our graphing calculator, and that would tell us exactly how many years it would take the rabbit population to reach that growth rate. So our population will be 5 whenever 10 divided by all of 19 e to the 1/5 divided by e to the t over 50 plus 1 is equal to 5. I'm going to count my parentheses just to make sure. So open, open, close. I've got 1 open. Open, open. I've got 3 open. Close, close, close. Okay. And we know that this has to be somewhere between 0 and 10. So I'm going to leave my window just like this. And we'll calculate our intersect. My population is between 0 and 10. My time, not necessarily. Okay, so I need to go further than this. We'll go up to 100 years and see if we cross by then. Not quite. There we go. Okay, so we can see our logistic curve kind of working its way out there too. Where I'm approaching an upper limit of 10, which is the top of my window right now. So I can calculate and intersect of our first curve, our second curve, and our guess. I'm going to say 200 years. Okay, so after 157.22 years, we hit a population of 5 billion rabbits. Any questions on anything we did for our sample problem?
No.
All right. Last part, just for those watching later. On this graph, I've got a couple different shapes. So if our slope is decreasing, but we are concave up, it would be shaped like this. So our slopes are, our function's decreasing, so the slopes are negative. But the slope is increasing, which means we're concave up. Here my slope is increasing, but my slope is also positive. Down here, my slope is negative and decreasing, so getting more and more negative as we go. And on the right side, my slopes are positive, but are decreasing, so getting less and less positive as we go. So I've got a couple physics examples for what this type of equation would look like if you're looking at the height of an object. So if I throw an object that it can float into a pool, when it initially falls into the water, the buoyant force is going to accelerate it upwards. So it has velocity, so it's still moving down, but the acceleration is positive, so the rate at which it's moving down is slowing down. Okay, there will be some point where the object stops falling, getting lower in the water, and starts rising. That's when the vertical velocity is now positive because we've changed direction. The acceleration is positive because our net force, that buoyant force minus the force of gravity, is positive. If we had an object that we dropped in the air instead, the vertical velocity would be negative if you just drop the object, so its height is decreasing. The acceleration is also negative. It's falling faster and faster and faster due to gravity. If you were to throw the object upward instead, you would start out with some vertical velocity, but gravity is pulling it down. And it's because that acceleration is negative, we end up with a concave down but increasing function until the object starts falling. Any questions on anything from this slide?
No.
All right. So let me just go for some vocab really quick. I've got some critical points and points of inflection that are all labeled on this graph, A through K. Which of these points would be relative minimums?
This graph of f of x.
This graph is the original function, yes.
Oh, okay. So we are looking for relative minimum, right?
Yes.
Then our relative minimum is D and H.
Perfect. D and H. What about relative maximums?
B, F, and J.
B, F, and J. Okay. What are C, E, G, I?
Each point of inflection.
Points of inflection at C, E, G, and I. What is the absolute minimum?
A.
A, since that's the lowest point possible on the interval. And what's the absolute maximum?
J.
J, because that's the highest point that's showing. Our relative extrema would be all of your relative minimums and maximums. Or B, D, F, H, J. I don't think we missed anything. Okay, when you're checking for the absolute minimums and maximums, or the absolute extrema, we can set our derivative equal to 0 to give us all of the critical points, and then check the start point and end point of our intervals into our original equation to figure out what our biggest possible y value and smallest possible y value is, and that should give us the absolute extrema. If you just had a function, you did not have a graph, how would you find the relative extrema?
Derive the function and set it equal to 0. And solve for x.
Okay, perfect. We'll have relative extrema as long as we derive it set it equal to 0, solve for x, and the second derivative is not 0 at that point. If we have a point where the derivative is undefined, then we won't have a relative extrema there, but it could still count as a critical point. Also here, our point of inflection is when the second derivative is 0 or does not exist, and the concavity changes. For points of inflection, we do have to change sign. For critical points, we do not have to. Any questions on anything from our curve sketching review?
No.
Alright, so since you're the only one here, instead of jumping into the FRQ right away, I'm going to jump into the questions that you asked me to take a look at from your homework.
Okay.
I guess I'll keep the annotations for now, and we'll save this as a separate file. Annotated. Okay, so you asked me to look at a couple Barron's questions. So for this first one, I've got a function that has a differential equation whose slope field is shown above. We're trying to figure out which of that functions it is. Our slope fields trace what the function would look like for the shape. In the center, this does look a little bit like a sine function. However, towards the end, it doesn't keep bouncing, right? Towards the end, we've got horizontal asymptotes. And because we've got horizontal asymptotes, I'll be looking for which function would have a horizontal asymptote both on the left and on the right first. So for part A, what is the horizontal asymptote of y equals x cubed?
None.
None. Okay, so this one cannot be A, since all of the possible solutions have horizontal asymptotes both at negative infinity and positive infinity, as x approaches negative infinity and as x approaches positive infinity. Okay, so not A. What about B?
At 0.
0. Okay, so B is possible. I'm going to hold on to B. How about C?
1.
1. Okay, so C is possible. I'm going to hold on to C. For D?
None.
None. Okay, so this cannot be D. And for E?
E. 0.
Okay, so I've got one horizontal asymptote as x approaches infinity is 0. What about if x approaches negative infinity?
Negative 20. 0.
Okay, also 0.
No. Oh, yeah. Is it?
I think so, because that negative's on the outside of that exponent, right?
Yeah.
If this was, if there were parentheses here, so then negative x would also be squared. If the negative is squared, then negative infinity would... That wouldn't matter either way, would it? It just have to be an odd power. Either way, we end up with horizontal asymptotes of 0. So we've eliminated A and D so far. Okay, now I'm going to look at the shapes of these different graphs. E to the negative x squared, if I was going to graph this, would end up being really big in the middle. This is 1 over e to the x squared. So when x is 0, this is as big as possible at 1. But on the outsides, I should be approaching whatever my horizontal asymptote is, in this case 0. So, does this match what's going on in the slope fields? Just for the general shape.
No.
No. I'm not biggest at 0, so not E. So we eliminated A and D based on horizontal asymptotes, we eliminated E based on the shape. C, as I approach infinity, what shape is this going to approach?
Can you say the question again?
What's the rough shape that the graph of C would look like?
Oh, a increasing exponential function.
What happens if I plug in 100? Or I'll say, what happens if I plug in 10?
Approaches or 10. 100 over 101.
Okay, 100 over 101. So I'm getting closer and closer to 0 on the right side as I'm in the middle. So if I plug in 1, what's going to happen?
1, then it will be 1 over 2.
Okay, 1/2. So our function looks something like, if I plug in 0, what's going to happen?
0.
0. Okay, so our function looks something like this, right? Where we're getting closer and closer to 1 at the ends of the graph, but then I'm hitting 0 in the middle. Does that look like our graph that we have right now?
No.
No, so not C either. Okay, so for B, if you plug in 1 right now, what's going to happen?
It will be 1.
Okay, if I plug in -1, what's going to happen?
Then it will be -1.
-1. Okay, so I've got something that goes like this towards the middle of the graph, which is good. But on the ends of the graph, we approach a horizontal asymptote. Redraw that last one. Which is what this function is showing. So B is correct.
Okay.
Okay, I'm going to jump down. Okay, here I've got a curve defined by this equation, which has a vertical tangent line when x is one of these values. So in order to find our tangent line equation, I need to know what dy over dx is. We're going to have a vertical tangent line whenever our first derivative's denominator is set equal to 0. So in order to solve for dy over dx, I can derive this equation in terms of x, which I'll end up with this. Okay, this xy term is product rule, and everything else is just power rule. Then I'm going to move everything that... Oh, I think I made a mistake here. I didn't actually change my signs. Okay, I need to change some signs, so we'll go redo this one from here. Oh. Wait. No, I still made a mistake. Okay, I need to change my signs on this one. So this will be -3x squared and -y. Okay, so from here, what do I need to do?
Divide x minus 2y for both sides.
Okay, perfect. So I can factor out my dy over dx. This will be x minus 2y. And then I'll divide that from both sides. Okay, so I'll have something like this. And so if that's true, then I'm gonna have a vertical tangent line whenever x minus 2y is equal to 0. Okay, so whenever x minus 2y is equal to 0, go back, because I can just change these signs here. This doesn't actually change anything that we'll need to do. I got really lucky with this. So whenever the bottom, the denominator of this function, is 0, then we should have a line of vertical tangency, and our denominator is 0 whenever x is 2y, which means x over 2 should be equal to y. So I'm going to take that x over 2 equals y, substitute that back into our original equation. Anytime I see y, replace it with x over 2. That gives us a new equation here that we can then solve for x. So, integraphing calculators. I've got x cubed plus x squared over 2 minus x squared over 4 is equal to 10. So I'm going to graph this on a 10 by 10 window again. Let's see if we can see where they cross. Okay, so I'm right at the edge of my line here. Oh, I need to be, because we have this equal to 10. Let me go up just a little bit more. 15. Oops. Did that for x, not for y. 15. There we go. Okay, then I'm going to calculate our intersect. So that is second calculate and intersect with our first curve, second curve, and our guess. And that should give us our intersection point, which gives us C, or 2.074. Any questions on 35?
No.
Alright, last one he asked me for was 45. So we're told that we've got some sort of radioactive substance. The amount remaining is given by this equation. I want the average amount that is not lost. The amount not lost is the amount remaining. So I'm looking for the average amount remaining. Since the substance remaining is the formula they gave us, the average of the formula they gave us would be our average value formula. So in general, this would be 1 over time 2 minus time 1 times the integral from time to time 1 of our formula. So if I want it during the second 100 years, so that's from year 100 to year 200, what would the average amount of substance be? And if we integrate that, we get about 5.78, which is closest to B. Any questions on what we did here?
Oh, I understood.
All right. Let me know later if you've got any other questions from the homework at any point, and we'll take a look at those too later on, okay?
Okay.
All right. My Teams is flashing, so let me see what's up. Okay, Kyle's just telling me he can't join. All right. So I've got about 40 minutes left. It should be enough to get through 1 or 2 FRQs, I think. So I've got this first one selected from 2015. I've got a figure, this is the graph of f prime that is showing, not the graph of f. The derivative of a twice differentiable function f on its interval from -3 to 4. The graph of f prime has horizontal tangents at -1, 1, and 3. The areas of the regions bounded by the x-axis in the graph of f are 9 and 12 respectively. So I'm going to draw that in really quick. This area from -2 to 1 is 9. And this area from 1 to 4 is 12 units. Okay, for part A, I want to find all x coordinates for which the graph of f has a relative maximum and give a reason for our answer. What do you think?
Oh, first I have to look for x coordinates when f prime is 0. So, and change its sign. So f prime x 0 when -2, 1, and 4. But negative, but 1 doesn't change the sign, so relative extremas are negative 2 and 4. And for negative 2, the sign of f prime x changes from positive to negative. So that's the relative maximum.
Okay, so you told me f prime x would be equal to 0 at the points x equals negative 2, 1, and 4. But you told me that negative 2 was the only relative maximum. Can you say why one more time?
Negative, because at negative 2 changes sign from at x equals negative 2, f prime x changes sign from positive to negative.
Okay, perfect. F prime x changes sign from positive to negative. Okay, perfect. For part B, I want to know on what intervals from negative 3 to 4 is the graph both concave down and decreasing? Concave down and decreasing.
Concave down and decreasing. First, the graph is decreasing at negative x equals between negative 2 and 1 and 1 to 4. And f prime prime is negative at between x equals negative 3 and x equals negative 1. And x equals positive 1 and x equals positive 3.
Okay, you said from negative 2 till...
Negative 3. Negative 2 till negative 1. 1, 1. Negative 1.
Oh.
And
Okay.
and from 1 to 3.
And 1 to 3. Okay, so I'm looking for when these two overlap, because I need both of them to be true.
Yeah, so the interval should be from negative 2 to negative 1.
Decreases and is concave down on the intervals negative 2 to negative 1. Are those included or not included for the bounds?
Included? Not included.
Okay, not included because at those points f prime is 0, not negative. Okay, so these should both be not included, which is our normal parentheses. I've got one more interval though, where both of these overlap.
From 1 to 3. I mean,
And
1 to 3.
And 1 to 3. Okay, I can't go all the way to 4 because then we wouldn't be concave down. Awesome. Okay, for part C, I want to find the x-coordinates of all points of inflection and give an answer. Give a reason.
First, f prime prime should be 0, which is the slope of f prime should be 0. So when x equals negative 1, 1 and 3, f prime prime is 0, and it changes sign.
Okay,
So these are points.
f prime prime is 0 and changes sign.
Yeah.
At x equals 1 and x equals 3. Okay.
And x equals -1 also.
Oops. This one. Okay, x equals -1, x equals 1, and x equals 3. Okay, cool. For part D, given that f of 1 is 3, I want to write an expression for f of x that involves an integral, and then use it to find f of 4 and f at -2. Okay, so let's get a general form first. F of x should be equal to
just integral. So for f of 4, the integral should be fx is 3 plus.
Okay, you've got it. So f of 1, which is 3, plus
Integral from 1 to x f t dt.
okay, f prime of some other variable in terms of that variable is fine. So when I integrate this f, I'll get f of x minus f of 1. So my f of 1's will cancel, and I'll be left with f of x, which is what we want. And then I'm going to use this to find f at 4 and f at -2. So let's do f at 4 first. F at 4 then should be equal to f at 1, which is 3, plus the integral from 1 until 3 of f prime t dt. What's the integral from 1 to 3?
Oh my. 1 to 3. Isn't it 1 to 4?
Oh, yeah, sorry. Going to the wrong point. Okay, integral from 1 to 4?
12.
The area of the region is 12, but what would the integral be?
Negative.
-12. Okay, so this will be 3 minus 12, or -9. Okay, a little bit trickier. I want to go backwards to f of -2. So f of -2 is 3 plus the integral from 1 until -2 of f prime t dt. But now my upper bound and lower bound are swapped. So what do I need to do?
Make it negative.
Make it negative.
It's the same as 3 minus.
Yes, I'm going to try to clean this up a
integral.
little bit, but this is the integral from 1 until x equals -2 of f prime t dt. Okay, so we can change our bounds as long as we multiply by -1. So this is the same thing as 3 minus the integral from -2 to 1 of f prime t dt. Okay, so I was told that area in that region is 9. So what should I write?
Oh, 3 minus 9.
So picture again.
3 minus -9.
3 minus -9. Or 12. Any questions on our first one?
No.
Okay. So I'm going to stop the official lesson here, I think, since you're the only one here. Is there anything related to calculus or calc 2 that you want to talk about? And if not, we can take a break. You'll have the last half hour to yourself. We'll just call it over for the class. But if you've got a topic you want to talk about, I can look up for your responses or see what I've got related to anything you want to work on.
Not really. I have no topics.
All right. If you change your mind, let me know. At any point, you can drop a topic into that chat that we created on Teams, and I'll add it to the list
Okay.
for future classes, okay?
Okay.
All right,
Thank
you're doing
you.
awesome. Thank you very much.
Bye-bye.
Goodbye.